Hello, welcome to my physics video. This is for Physics 102B, Chapter 17 on electric current, resistance, and circuits. And these are the homework solutions. We'll start with number 35. Find the resistance between the two ends of an aluminum wire, 0.25 meters long and 1 centimeter in diameter. We're going to first write out the given information, the length in MKS units, 0.25 meters, and its diameter is 1 centimeter, therefore its radius is 0.5 centimeters, and we're going to use the resistance formula. Resistance is resistivity times length over cross-sectional area, and that cross-sectional area is pi r squared. We'll need the resistivity of aluminum. We can look that up in the table in the book. And that's 2.75 times 10 to the negative 8 ohm meters, times the length, divided by pi. The radius squared, remember we need all of this in MKS units, so 0.5 centimeters becomes 0.005 meters. We're going to square it, and we get a resistance of 8.75 times 10 to the negative 5 ohms. It should be very, very small, as you see here, and that's because we're talking about aluminum, which is an electrical conductor, so we expect a very low resistance for a wire. Number 36, a platinum wire is originally at 20 degrees Celsius. Find the temperature required to raise its resistance by 1% and by 10%. So we're looking at the temperature-dependent resistance or resistivity. Now we have this equation right here, and the equation given in the book and in my lecture is the rho equation. So it's the resistivity equation, rho equals rho naught times 1 plus alpha times the change in T. But as you saw in example 17.4, resistance, since it's proportional to resistivity, we can replace those rho's with the R for resistance. It's the same thing. And the question is asking about, we have a given change in resistance, a certain ratio, and what is that temperature? So let's solve this equation algebraically. For T, we go through the steps. We divide both sides of the equation by R naught. Then we're going to subtract away the 1, we divide by alpha, and we end up with this equation for T. And we're going to plug in for part A. It says that the resistance is raised by 1%. So we can think of that as the ratio of R over R naught is 1.01, which is 101%. So we're going to plug in that ratio, 1.01, into the equation. We're going to need the alpha, the coefficient for platinum, which is 3.9 times 10 to the negative 3 Celsius degrees, or per Celsius degree. And remember that there's also the plus T naught on the side. So whatever this fraction becomes, plus 20 degrees Celsius, and you should get 22.56 degrees Celsius. So it's with this slight temperature increase that the platinum wire its resistance will go up by 1%. What about for part B, raising it by 10%? We expect it's going to be a higher temperature. So the ratio of resistance over initial resistance is going to be 110%, which is 1.10. We plug that into the equation, and you should get a total temperature, or a final temperature, of 45.64 degrees Celsius. Number 38, an electron beam carries 1 milliampere. How many electrons pass a given point each second? And the way we're going to relate current to the charge, or to the number of electrons, is first let's think that current by definition is charge that passes a given point per time. And that means charge is current times time. Now we can relate this to the number of electrons. I'm going to replace in this equation charge with the number of electrons times the charge on a single electron. And you remember the charge on a single electron, that's the elementary charge, 1.602 times 10 to the negative 19 coulombs. It is negative, but in this problem we're more working with just absolute values, so I'll just keep it positive. And we're going to solve for n. N equals current times time divided by the elementary charge. And so we plug in those values. 1 milliampere is 10 to the negative 3 amperes. The question is asking about a time of 1 second. Divide by the elementary charge. And we get 6.2 times 10 to the 15 power electrons. Number 42 involves nichrome. Nichrome is a nickel-chromium alloy used in heating applications like this toaster because it has a relatively high resistivity and it heats up when current passes through it. So this toaster wire, initially at room temperature, carries 2.75 amperes. Immediately after it's turned on, after the wire heats, the current drops to 2.46 amperes. What is the temperature of the nichrome then? And we have to think, why is the current dropping? Well, that's because the resistance is changing. So let's explore that. We have this equation from a previous problem, the temperature related to the ratio of old to new resistances. And so if we want to know what the new temperature is, we have to get into what is the new resistance, and particularly what is the ratio of new to old resistance. Now, we're not given the resistances, but we are given the current, so let's use Ohm's law. Current equals V over R, and voltage is going to be constant. And so the new resistance is voltage over new current. Old resistance is voltage over old current. And so if we want to get at this ratio, R over R naught, that's going to be, we're going to divide V over I and divide it by V over I naught. And so what we end up with is that it's the ratio of the old current over the new current. And so now I'm going to approach the equation at the top of the screen and replace that R over R naught with I naught over I. And those are values that are given in the problem. Don't mix up which is the old current and which is the new current. So the old current is 2.75 amperes, the old is 2.46 amperes. Plug those values in. Remember to add the 20 degrees Celsius. The question isn't asking about the change in temperature, but rather what is the new temperature. And so we can see 308 degrees Celsius. Hot enough to get our bread nice and toasty. Number 52, you can see I've drawn the circuit diagram at the top. A 34 ohm and a 45 ohm resistor are in series. Find the equivalent resistance. Find the current when the series combination is connected across a 7.5 volt battery. All right, resistors in series are very easy. They just add up. So here I have the equivalent resistance. In some formulas you might see in the book or in my own lecture notes, I write R sub S, but here I've written R sub EQ, just the equivalent resistance. And they just add when they're in series, 34 plus 45, and that becomes 79 ohms. From there, we can answer part B, the current with the 7.5 volt battery. So we're going to use Ohm's law. The current is 7.5 volts divided by that 79 ohms, and we get 0.0949 amperes or 95 milliamperes. Number 53 involves two resistors in parallel. You can see the diagram at the top. Find the equivalent resistance. The parallel combination is connected across a 12 volt battery. Find the current supplied by the battery and the current in each resistor. So if you look at the diagram, there's going to be a current drawn from the battery. And that current is going to be determined by the equivalent resistance of both of those resistors. So we need to find that equivalent resistance. Now, whatever that current is, imagine like pipes of water, it's going to all flow and it's going to get to this junction, this node, and some of it's going to go down this way and some of it's going to go this way. And the current is going to divide up in proportion to those resistances. The current will tend to go towards the path of least resistance. And in this problem, we'll figure out what those currents are. and then some of it goes down this way, some of it goes around this way, and the full current joins up together, and whatever current was supplied by the battery continues on into the negative terminal. Let's figure out the equivalent resistance, and we're going to use this formula. When they are in parallel, the reciprocals add, and they give the reciprocal of the equivalent resistance. So 1 over the equivalent resistance is 1 over 250 plus 1 over 370. And you can do that math. Just when you get the value, make sure that you take the reciprocal of that, and you get 149.2 ohms. And you can judge, you can make a reasonable assessment. Does this sound about right? It should generally be in the same ballpark. So 149 ohms is in the same ballpark as 250 and 370, but also it will be less than any one of those individuals. So the lesser of those two resistances is 250, and the equivalent resistance is always going to be less than that. So 149.2, that checks out. Okay, now that we know that, let's find the current. And with this equivalent resistance, you can imagine it's like in the circuit pulling out both of these resistors and replacing them with a single 149.2 ohm resistor. So now we're going to use Ohm's law, voltage over that equivalent resistance, and we get 0.080 amperes. That's the current supplied by the battery. Now, when that 0.080 amperes gets to this node, it's going to split up. Most of it is going to go through the resistor with the lesser resistance, this 250 ohms. But let's see how that breaks up. Each resistor has a 12 volt difference. That actually is a characteristic of resistors that are in parallel. They have the same voltage, so 12 volts. We're going to use Ohm's law to figure out what the current through each one is. So through that first resistor, it has 12 volt drop across it divided by its 250 ohms, and we get 0.048 amperes. The second resistor is a 12 volt drop divided by 370 ohms, 0.032 amperes. We can check our work. Notice that they both add up to the original 0.080 amperes, and also notice that the resistor with the lesser resistance, 250 ohms, is getting more of the current. Let's take a look at number 65. A 150 ohm resistor is across a 24 volt battery. Find the energy supplied by the battery in 1 minute. So it's asking about energy and time. We have an equation that involves power. So let's think about these different relationships that we know, that power is energy divided by time, which means that energy is power times time. We're given 24 volts, resistance is 150 ohms. We're going to use the equation that power is V squared over R. You have 3 different versions of this equation. Power related to voltage or current or resistance, some combination of those. We're going to use the one that uses the given information. So power is V squared over R. You can plug in the values. Don't forget to square that 24 volts. And we get a power of 3.84 watts. Now we're going to use the equation that energy is power times time. So 3.84 watts, and remember what a watt is. It's a joule per second. So 3.84 joules per second times 60 seconds, and that's going to give us 230 joules. Number 69. A hairdryer consumes 1750 watts when connected to a 120 volt source. Find the current in the hairdryer, how much energy is consumed if the dryer runs for 10 minutes, and then compute the monthly cost if the hairdryer runs for 10 minutes each day at a cost of 15 cents per kilowatt hour. All right, we need to take these steps in order. We're given the power and the voltage, so we're going to use this power equation. Power is current times voltage, and that means current is power over voltage, so 1750 watts over 1240 volt, or 120 volts rather. And we get 14.6 amperes. That's question A, find the current. Now, how much energy is consumed if this hairdryer runs for 10 minutes? And so From the previous problem, we had energy is power times time. So we're going to take our 1750 watts, and remember again, a watt is a joule per second. We're going to multiply that by 10 minutes, which is 600 seconds, and we'll get 1,050,000 joules, and I've just put that as megajoules here, 1.05 megajoules. Now, for part C, we're going to use that 1.05 megajoules every day. It says compute the monthly cost if the hairdryer runs for 10 minutes each day. And so we've already found the energy consumption for the day, and now we're going to multiply that by 30 to get the monthly cost. And so let's, because the problem is giving the cost in kilowatt hours, and that's standard for what power companies do or electric companies do, let's get this in kilowatts times time. So energy is, you can think of it as, so 1.05 megajoules, that's what I had on the previous slide, is 1050 kilojoules. And let's turn those joules into watt seconds. Just like a watt is a joule per second, a joule is a watt second. And this will actually make it go more easily if we think of that joule as the kilojoules as kilowatt seconds. Now for 1 month, we're going to assume 30 days. We're going to take that 1050 kilowatt seconds, multiply by 30, and we get 31,500 kilowatt seconds. Now I want to emphasize, I'm usually inclined to go with MKS units to keep it in joules or kilojoules, but I'm doing it in these awkward units of kilowatt seconds because that is how the electric company charges. It charges by units of kilowatts times time, actually kilowatt hours. So what we found is that in this month, this hairdryer is going to consume 31,500 kilowatt seconds. And now, because the company charges in kilowatt hours, I want to do the conversion. So we think back to chapter 1 of first semester physics, how we do unit conversions. We have kilowatt seconds, we want kilowatt hours, and then we want dollars out of that. And so I set up the given information, and then I want seconds to go away and us to be left with hours. So 1 hour over 3,600 seconds, the seconds will go away, and we're left with kilowatt hours. And then I want this in dollars, so $0.15 per kilowatt hour. So all of the kilowatts and time goes away, and you're left just with dollars. So $1.31 is the cost to run this hairdryer for $10, or I'm sorry, for 10 minutes a day for a month. Number 7.4. We're looking at RC circuits. These are the time-dependent circuits that charge and discharge over a given amount of time that's determined by the resistor and the capacitor. It says, how large a capacitor should you combine with a 450 kilo ohm resistor to make an RC time constant of 25 milliseconds? I want you to know that the time constant of an RC circuit is resistance times capacitance. So 25 milliseconds is 25 times 10 to the negative 3 seconds. It's telling us we're using a 450 kilo ohm resistor. And so let's solve for capacitance. Capacitance is the time constant over resistance. Here I've plugged in those values, and I get 5.5 repeating. We'll just call that 5.6 times 10 to the negative 8 farads. Now let's put this in units with prefixes, the way it'll be listed on the capacitor, so we can call that 56 nanofarads. Number 75. A 300 picofarad capacitor, initially uncharged, is in series with a 175 mega ohm resistor. The series combination is then connected across a 6-volt battery. Find the charge on the capacitor after these given amounts of time. All right, so let's write out the given information. We need this in MKS units. So the capacitance is 300 pico. We're going to call that 10 to the negative 12 farads. The resistor is 175 times 10 to the 6 ohms. Let's figure out right now the time constant, RC, 0.0525 seconds. This gives us a ballpark estimate of what timing are we expecting here. And so that is 53 milliseconds, 52.5 milliseconds. And so it's going to ask about what's happening after 1 millisecond. Well, that's not that much time that's taken place after 1 millisecond. Part B is going to ask about 10 milliseconds, and that's a little bit of a time constant. And then 100 milliseconds. So the capacitor's originally uncharged. It says it's across a 6-volt battery. Find the charge at these given times. So we're going to use the time-dependent equation for the charging of an RC circuit, and there it is, where my script E is the voltage across it, and little e, of course, is the base of a natural logarithm, and we're just going to plug the values in. So 6 volts times the capacitance times all of that, and I've left the thing I just called all of that, 1 minus e to the negative time over the time constant. I've left that in brackets just so we can see what percentage of the total charge we're looking at. So you can see that bit in brackets becomes 0.0189, meaning it is less than 2% charged. Not that much time has gone by, so it's got less than 2% of its maximum charge. And so that's going to be 34 picocoulombs. Now, part B asks for it asks for 10 milliseconds, or 10 to the negative 2 seconds. And so we can plug into that same equation that's up here. And the bit that I had in brackets is 1 minus 0.08266. So it's about 17% of its maximum charge. And you should get 312 picocoulombs. And then the next part, 100 milliseconds, or 0.1 seconds. And it's got most of its charge, actually about 85%. When you plug in the values, you should get 1.5 nanocoulombs. Question 78, again, deals with a capacitor that's initially uncharged, series combination with a resistor with a 24-volt battery. What is the maximum charge it will eventually attain? And how much time does it take for it to reach 90% of that maximum charge? Well, we have the given information. Part A, the maximum charge is just the voltage times the capacitance. And so you think of, imagine this is not an RC circuit. Imagine it's just a battery with some voltage and the capacitor. That's what the maximum charge would be. So the voltage times the capacitance, elsewhere in the chapter, we've just simply seen Q equals VC. And so we get 6 times 10 to the negative 7 coulombs. And now it's asking how much time does it take to get to 90% of that? And so we use the charging, or the charge equation for a charging RC circuit. And I'm replacing the EC with just Q max. That's what we solved for in part A. And so let's plug in the values that we know. Q over Q max, I didn't explicitly write it out here, but if we take this equation and divide both sides by Q max, we have the ratio Q over Q max, and that is 90%. So 90% equals 1 minus e to the negative t over RC. And we're going to go through the algebra. I've added e to the negative t over RC to both sides of the equation. I've subtracted 0.9 from both sides of the equation. So now we have e to the negative t over RC equals 0.1. And now in order to solve for t, we need to turn this into a logarithmic equation. So the logarithm base e, that's natural logarithm, of 0.10 equals negative t over RC. And then we go ahead and algebraically solve for time, and we get 0.083 seconds, which is, if you think back to, you can solve for the time constant, and you can see that that's roughly, oh, here I've done right here, time constant is 0.03625. So we're looking at about 2.3 time constants. Here I've drawn a graph of charging, what you can expect for any RC circuit. After one time constant, there it is, R times C, you get 63% charged. After two time constants, it's 0.86 or 86% charged. After three time constants, it's 95% charged. And so 2.3 time constants were somewhere here in between those. And so, yeah, 90% charged is going to be about 2.3 time constants. And that is it for the Chapter 17 homework. Have a great day.